we are gonna do another question, which is the minimum number of coplanar vectors of coplanar vectors having different magnitude having different magnitude can be added to give a zero resultant is, so the options that we have is 2, 3, 4 and 5. So very simple options if you think about it. And we need to find the answer. Just by looking at the question, I can tell you that the answer is 3. And I'm going to tell you why. But before that, I'm going to tell you how people write numbers. So just because I wanted to. So number, like many teachers write this in various ways. Some teachers just write it as a hash. So this will be considered as a number. So like number of people. So they would write it like this. So number of people. Sometimes hash is represented to represent number. Sometimes NO or is represented to represent number. But I like NUM since NO also sounds like no. So like what are you supposed to write? That's why I'm telling you this. So now let's see why this is the answer. I would like to show you that 3 is possible and 2 is not possible. And once you know that 3 is possible, it's going to be the lowest one very easily. So let's understand the some terms. What are coplanar? So coplanar meaning same plane. When I mean same plane, I mean to say, like as you can see, your screen is one plane. So your bench, or if you have a bench or you have something, that's one plane. Your hand, if you move your hand up and down, that's going to be different planes because your hand is moving to several planes. So plane is basically a flat piece. You can think of it as a flat piece of paper. Um, so to do this, first of all, let's do with two vectors. Let's Since there is no one vector, let's think about it for one vector. So let's say I have a vector. Let's make this one vector. Um, this vector, and when doing this kind of question, we generally don't consider zero vectors. So we are not going to consider each vector to be a zero vector resulting in the net resultant to be a zero vector. So we are not doing that. So let's say you have one vector. Even if you have any vector, any direction, even smallest, largest, it does not matter. It's just never gonna give you zero. So this can't give you zero. So this can't give you zero. This can't give you zero resultant unless this is a zero vector. Um, but we are not considering that case. So unless zero vector, but we are not considering this. So I'm not going to write this. So let's write not considering all as zero vectors. So we are not considering all vectors to be zero vectors. So that's what I'm trying to say. Uh, so this is for 1. So if there is only one vector, this can't be zero resultant since even any vector is going to have a magnitude that has a magnitude. It cannot be in 0 since there's nothing that's going to counteract that. Let's say we have 2. So let's say we have 2. And I'm deliberately trying to find a way how you make this. So let's say I have this vector. This vector can be rotated in any way, can be any size. It does not matter to me. And let's say this is my vector. And if I have to make 0 resultant, I just need another vector that's exactly the same magnitude but just the opposite direction and place it over here, or place it anywhere. It does not matter. I can place it anywhere due to parallel transformation, and in this case this will lead in 0 vector, so leads to 0 resultant. So the obvious question that you must have is, isn't the answer 2? Then why are we doing 3? The answer is pretty simple. The question is the minimum number of vectors that can having different magnitude. But in this case, to cancel the first vector, so this, let's say this vector, every vector that you take, the first vector, you need other vector that has the same magnitude but that is opposite in direction. That's the fundamental problem. If that was not a problem, there wouldn't be a need to do this. So if I take any vector, so let's say I take any vector, I can take this vector, that vector, that vector, it does not matter. As long as I have same magnitude and reverse direction, so I will get 0. So that's the only way to get 0. That's only way to reach 0, but it has the same magnitude, that's the problem. But that has same magnitude. So if there is a question about vectors that have that, or if there is a question that says how minimum number of coplanar vectors to give 0 resultant, there is no specification on magnitude, you can say 0, 2 vectors will be the answer. Now let's take why 3 vectors is gonna be the answer. To understand this, let's take the most simplest example, since even if we have only one example, it's gonna be fine, as long as it works. So let's say I have this vector and I'm gonna make it so that each vector is gonna be different. So if we had 2 vectors, let's say we have 2 vectors, let's say we would have to do this, right? We would have to do this. But who says that this blue vector has to be only one vector? What I'm going to do is I'm going to make 2 vectors of different magnitude. Let's make this green, and let's make sure that this vector is like 1 unit long, whereas this vector is 2 units long. So as you can see, these 2 vectors will give a resultant that is of 3 units, which will cancel this one out. So this leads to 0 resultant and has different magnitude. So a question that you might have is, if vectors greater than 2 have the same magnitude, can they still result in 0 vector? And the answer is yes, since you can always rotate this vector. So let's say there is a vector that is equal to this vector, and I just put 2 vectors like this. So think of these vectors like that, and if they are like that, the resultant that you're gonna get is gonna be this vector, which is gonna cancel that vector out. So even if you have vectors of same magnitude, it can still give you 0 resultant. But in this question, we are only checking if the minimum number of coplanar vectors having different magnitude that can be added to give 0 resultant. So if you understand what I'm trying to say. So this is gonna be it for today's video. So in the next video, we are gonna check out another question. So till then, bye bye.